All right, 6 steps for planning and implementing and winning construction QA strategy. So before we actually get into the meat of today's webinar, go ahead. A couple of housekeeping items. Number one, first and foremost, participants are going to be muted during the presentation. Number two, questions. We do have a wonderful chat functionality in GoToWebinar. So at any point, if you guys have any questions or anything, feel free to type in the chat box. We'll address those questions at the end of the webinar. Yeah, that basically rolls into point 3. Again, we'll answer questions towards the end. Point number 4, this is going to be recorded, so we'll send out the recording to everyone afterwards. So if you come in late, don't worry about that. You'll definitely have the recording. And then that also rolls into point number 5. So with that, let's introduce who we got for today. So I guess first of all, I'll let James Norris introduce yourself.
I'm James Norris, also James Norris. I'm in charge of, well, I work with Trevor in industry strategy. My past was, I worked for a large design build company until 2019, before I moved into software and hardware with ClearEdge. And we had a consulting side that did scanning and modeling. We had an operations technology team, team specifically supporting architecture with Revit, 3D coordination, and also scheduling, like how we build buildings, having dashboards to ensure buildings were being built on time and were healthy and were properly sequenced. Yeah, and now we spend our time like meeting with clients and ensuring that we're not like building a software in search of a solution. It's like the big mantra is let's learn and then go build the thing, and that's it. So
perfect. Thank you, James. I guess Justin, you want to go next?
Sure. So I'm Justin Domer. I've been with ClearEdge for about 8 years, and in that time, it's been kind of a wide variety of stuff that I've done with ClearEdge. So it's been working with customers internationally. It's been working on the development side. My current role is product manager, so I'm the product manager for Edgewise, but very familiar with Verity and been working with that since we created it. And yeah, I like rock climbing and slacklining. And just trying to make things better in the industry.
Perfect. And I guess last but not least, your host myself, I'm Trevor McGough. I've been at ClearEdge very, very long, ever since it was basically 4 people in a small office when we were a little startup. A little bit about me is my background is actually in GIS and cartography, so map making. Fun fact about me is even though I am a cartographer, I absolutely have a horrible sense of direction, which makes me great in that regard, because if I can follow my maps, that means anyone can. So with that, let's go ahead and actually dive into today's webinar. So first up, we got James Norris talking a little bit about optimizing data for collection for verification. So James, go ahead and take it away.
Yeah, all right, so I think before we dive into, the ideas of verification, whether it's automated or visually, like, a really key component is using the right hardware, depending on what you're trying to achieve. There are really kind of 3 sets of hardware from the scanning side. Yes, there are drones, and you can have an RTK tied to that, but we're just going to focus on effectively like things that a human physically is walking with for today, just because, with drones, you're looking down on a thing kind of at an angle, which can be good. But we're going to focus on things that create a lot of coverage for visual verification. So for automation. So you've got 3 camps, right? Terrestrial scanners, and these are, we say terrestrial, these are things that sit on a tripod that you move around, like a Faro, an RTC, a GLS, etc. Then you have SLAM-based systems. There's a wide array of SLAM. Like, you've got Zebribos, you've got the Navis, you've got the Heron, et cetera, et cetera. I think in terms of verification and validating his work being installed correctly, like if you're walking on a floor in a high rise, or certain, we're going to kind of focus on these two SLAM systems because they're tying into control. You can see the data in real time, and that's going to matter for that kind of workload because today is about verification. And then there's hybrid instruments, right? So an example is like the GTL 1200, where it's a robotic total station. These kinds of things are starting to come out, right? Where they're robotic total stations and a scanner all in one. So when you're not using your scanner, it can still be used for layout on a job. So it's not just sitting in an office collecting dust. But it depends on what you're trying to achieve. So with terrestrial scanners, they are great for capturing large amounts of data at high precision. And when we're thinking about large amount of data, square footage is relative to what you're trying to capture. A central utility plant with lots of pipes, you're gonna have a lot more setups that are closer together. So and then open areas, you can, like a factory that has no walls or whatever, you're gonna capture a lot more square footage. So really it's more like scans per day, right? So normal pace is about 100 scans. It can be faster or slower. Depends on the scan settings you use, with a precision of about 1/8 of an inch. I think that, again, it depends if you're checking steel, or you've got if you've got or MEP penetrations, like it does matter to be fairly close, because that, plus or minus 1/8 of an inch is probably what you're going to want. You can do a quarter if you're checking for walls and but concrete install, you really want to know really to the nets, but like how accurate you are. The thing with terrestrial scanners is they really don't have any ability to get on to control, minus so the ZNF and the P series, you can tie in the P series robot from Leica, Zoll and Frelick, I believe, also can tie on to a control point. But a lot of people commonly will use a Faro or an RTC. They don't. You have to do that back in the office. The problem with that, the good thing is you can fly, right? You're scanning. The bad part is, meaning you're not doing registration right in the field, but the bad part is if you have an error. So let's say the control that you're tying into is wrong, you're not going to know, and then you're going to have to come back out to the job and scan again, or tell someone to fix a control point. So it can be very beneficial to be able to tie into control while you are in the field, and looking at software and hardwares that do that. But again, it all depends. The ideal scenario, these are great for large projects where accuracy is really high. Medium-sized jobs too. You can do 10 scans, you can do 150 scans in a day. It's just, and the data will be highly accurate. But again, you're limited by the inability to get onto control in the field and knowing is it right. And that can be a big issue, especially for very large jobs. And that's what we're going to talk about, these other systems and how they communicate and tie to each other. So SLAM. So mobile scanners like the Navis VLX or the AC Twin are probably the best in class for the building construction space. And the main reason is that the algorithms for making the scan data very clean and kind of not having as much of a drift problem is really great. And all different SLAM systems can be good, but if you're capturing like a big floor, you want something that has algorithms and things that can kind of remove the issues of drift. And what we mean by that is, again, when you're walking around with like a mobile scanner, it's kind of like it's registering to the last frame. So it's not like there's this one scan that knows exactly where it is in the world and all of the things are tying to that one scan. They're registering to the frame prior. So the issue with that is you can collect a lot of error, and by the time you get to the other side of a building, you might be off by 3 or 4 inches. It can happen, especially if there's not a lot of unique geometry between the little frames, because they just don't know where they are in the world. So the reason these two are really good, in relative to doing like installation verification, like have things on this floor been installed right, or is this design right compared to the scan, is they can get tied into control, right? So if you've got control points, survey points that the Revit model or whatever kind of modeling software you're using, whether it's CAD, doesn't matter, it has a coordinate system, you can tie into those while you're outside in the field, and that really removes a lot of that error, just really critical. The thing you can't do, you still can't create control points. So and that can matter a lot if control points are not like within the field of view or they're not enough. So many times people will hire a surveyor, or on your job site, you'll have control points you can tie into. But you need enough of them in order to properly do that. The thing, in the ideal scenario for that would be small to large projects where you need medium accuracy, right? So we're thinking 1/4 of an inch is like at best, and that's more with like an M6. You're looking a lot around like the 1/2 inch area, sometimes 1/4 of an inch if you're really tight with tying into lots of control points, maybe. So I think of that more in terms of if you are doing verification, you just need to understand that you may be off. You play 1/2 inch to be safe and be okay with that. That may or may not be okay. It might even be more than that. It could be up to 1 inch. So it just really depends on the play you have. And then there's hybrid scanners and total stations. Because it's a total station, you are going to be as accurate as the total station itself. So the cool thing with that is when you're on like a high rise or data centers, when you're trying to scan and say, is stuff getting installed correctly? Like these jobs are huge. And so these control points are very far away. So with a terrestrial scanner, right, you can set a sphere up. Let's talk about like some of these, if they support spheres. You set those up on a control point, but that control point, if it's like farther than 70 meters away, or or really even less than that, I'd even be safe with 50. Again, it depends on the scanner, but generally speaking, that's kind of the thing. You can't rely on that control point anymore because the scanner is only so accurate out to a point. And the problem with that is job sites are big, and these control points that you're tying into to tell the first scan exactly where it's at is limited by that distance, which means you need points up on your floor. You may not have them. So this is just something to take into consideration. With hybrid instruments, at least you can shoot, 500, 600, 700 feet away, and then it informs the scanner exactly where it's at, and you can shoot a scan. Great for capturing medium amounts of data with high precision. Scans per day at a normal pace, it's about 50 for the GTL. Precision is eighth of an inch. And you're getting onto control in the field. It's pretty common, like more for you're doing verification on a daily basis and building the building as it's going up and shooting and saying, are things right? It's a great instrument. Because you also know right then and there if the scan is right, and if in cloud to cloud, it will tell you if like there's a bust in your registration or a bust in the survey control. But if you're trying to like scan a whole hospital in a day, you're going to use more like a terrestrial scanner or a slant-based system from one of these two. But if you're doing 10 scans, 30 scans, maybe max 50, you don't need to do that. Just depends on what the most common occurrence is. So I always say when you're doing verification, you're buying an instrument, think of it as what's the most common job you're doing, and then the other thing, just rent those things, whatever that is. Next slide. For visual verification, you're definitely going to want to turn, if you're doing terrestrial scanning or just, you want to turn your density up to 11, like the spinal tap thing. You want as much data as you possibly can get. Too much, there is a such thing as too much. So like resolution settings on different hardware, they might say like low, medium, high, or they might say 3.1 millimeter, 11 millimeter, 12.1, 20, things like that. Like medium is fine. Medium is fine for visual verification, and that means like you're going to go scan and you're going to go drop this into Revit or give it to an architect, or you're going to give it to whoever is doing clash detection. They're just going to do visual verification. Give them 11 or 12.1 resolution, which is normally the medium setting. And if you turn on the camera, that also helps, but that also adds time, normally about a minute to a scan. And what really matters is intensity value of the scan data, meaning you don't really need photos unless they ask for them. Or they might need photos if they're modeling from it. And that's where it very much helps, because it tells them what kind of material, color, etc. But for verification, turn the photos off. Scan times for that are anywhere between 1 to 3 minutes. SLAM, very different, right? Because you're just walking. But again, the thing is, you have to have control, and you can still suffer from drift and error. So you have to be very careful about what you're using it for. I would probably still suggest, at least right now, I'd probably suggest terrestrial scanners if your tolerances are fairly high. And then automated verification with Verity, the cool thing is we've designed with these amazing genius developers. For Verity, you don't need high resolution scan data. We only need enough points on different planes to understand, hey, where is this thing actually been built? And it's like 12 points, really, that need to hit like an element, right, on different planes. So the great thing about that is you can really turn the resolution down super low and get the data you need and get effectively pretty much the same results. And this cuts your scan time way down. And that matters a lot when you, let's say concrete's getting poured in like 3 hours. You're not going to be out there having high density scans. You're just not going to have enough time. And a big part of why we did this is there's this time problem in the field. Like there's not an extra day for QA and QC. Because buildings in the United States, we like to build them faster than they've been getting designed, right? It's the world we live in. So the faster you can get on and off a deck or the space that you care about, the better off you are. And it's 1.5 to 2 minutes per scan station, but you can cut that down to like 30 to 40 seconds with like an RTC or GTL. I don't know if Pharaoh's at, probably pretty low too, I would have to think, fairly much the same. So that's it.
Sweet, let me go ahead and hit the next slide button, and this will be my piece, which is applying hybrid registration techniques to ensure accuracy. So my other big claim to fame at ClearEdge 3D is I handle a good chunk of pretty much the data processing, so I've seen point clouds from everywhere. I mean, you name it, I've probably seen a point cloud. Part of that is I've also gotten pretty good at fixing data. So one of my big gripes, especially I guess you could say in the, as scanners have gotten better, especially like registration, well, to be blunt, Cloud to Cloud. Cloud to Cloud is an absolutely fantastic piece. You can rip through very quickly, and basically as scan data comes off the scanner, it automatically, will take itself and register back to your previous scans, and you get your beautiful point cloud, when you're done. That is awesome until it's not. And what I mean by that is something like this: repetitive design. Long hallways, warehouses that are very open, large open fields, basically things that are very geometrically sparse that can cause absolute havoc with cloud-to-cloud algorithms. Especially as there's like a big push to use these algorithms, one of the things I really want to highlight to people is, hey, there's going to be times when these algorithms will fail. Fun or not so fun story is collecting a point cloud on a project, long hallway. That hallway, when we were taking a look at the point cloud data afterwards, ended up being about another 2 feet. And then we're all scratching our heads and thinking, hey, which one's actually the truth? The model or the point cloud? Turns out that very long hallway, since it was very geometrically sparse, there was nothing the point cloud could really, or the cloud-to-cloud algorithm could really register itself on. So it ended up basically lengthening it. And I think that shows right there a great example of when cloud to cloud is just not appropriate to use. And that's where we're going to talk a little bit about getting and kind of applying these hybrid registration techniques to make sure your point cloud data is the best possible for actually doing the QA/QC process. So here's actually a great example of a project, long hallways. This is, right here you can see kind of towards the right side of the screen, up there at the top, as well as in between these individual lobbies. It's basically all long, very geometrically sparse hallways where there's not really a lot of stuff for a cloud-to-cloud algorithm to do. In fact, when we first tried this, it ended up actually playing a little bit of havoc with kind of the instruments we were using. Again, since there was nothing it could register itself on. It's all blank, if you will. So this is where having an instrument, for example, like a hybrid, where you can actually get on control and establish those control points. So in this case, what we ended up doing is we took anchor scans. So these little blue dots represent the anchor scans we took. And so setting up on a known point, we ended up shooting and creating these basically control scans using the GTL 1200 in this case. And those anchor scans then acted, well, as an anchor. And then we went back through and just cloud to clouded the rest of this. So the real power of having a control system is that when you generate these anchor scans, that represents then the ground truth. And so whether or not you're using a traditional, say, for example, like an RTC 360 or even a SLAM system like a Navis VLX or a Heron, you can then kind of get the best of both worlds. You can run through, create very high accuracy data, but then you can use one of those faster scanners to basically run through and kind of fill in the gaps kind of in between those sections. And that way you're really kind of getting the best of both worlds, where you're getting fast capture times as well as very accurate positional data. And so being able to use and apply that hybrid registration technique, especially in kind of more things like I would say hospitals or stuff that, usually there's not a lot of stuff going on for a cloud-to-cloud algorithm. That's really how you can defeat those challenges and really collect, good quality point cloud data for use with later on down the road, actually doing construction QA/QC. So the other key thing that I want to talk about is not just the point cloud itself, but the alignment with the coordinate system. So this is another one where the kind of, I guess you could say, like the devil's in the details, if you will. Aligning to control and not to the design model. So a classic thing is if the point cloud's not on control, there's nothing, it's just sitting out there 0, 0, 0, is dragging it over by hand and then saying, hey, looks good enough. Big gripe of mine is, when you're doing that, you're introducing human error into the equation. And then depending on who and kind of what you lined it up on, that can basically cause like a whole bunch of, downstream issues with, hey, is that actually correct, incorrect, yada, yada, yada. So the big thing is having that control network established that basically represents that ground truth that both the design model and the point cloud are aligned to, instead of just aligning the point cloud to the design. So the big example of that is like right here. If we had just plopped the point cloud on the design model, everything probably would have looked good. A great example, kind of thinking here is one project we did. We actually kind of did that where we plopped the point cloud, got it best fit to the design. All the columns look great. Turns out when we actually kind of looked and kind of did a second pass at it, by aligning it to the design model, we actually ended up redistributing the error. And that error ended up allowing all the columns to actually pass within tolerance. When we got it correctly aligned, turns out 2 of the columns were actually way more out of tolerance than we thought, and the other 2 were actually way more intolerant, or a lot closer to the fit. So that right there is kind of like a key example, is when you're doing a best fit of the point cloud to the design model, you can basically end up redistributing your kind of error, and that can hide a lot of the otherwise deviations and errors that would then pop out if both were instead aligned to a control system. And that's what this little graphic right here is trying to represent, showing that when both are correctly aligned, a lot of these little things will start popping, and then that's how you can get the best out of your QA/QC. The other one, this is another key one, is Revit and Navisworks coordinates. I think anyone who's worked in Revit, Revit's got like, what is it, James? It's got like 3 different coordinate systems. So
Yeah.
being able to, So being able to choose the right one, either upon export or import, again, kind of similar to any of the CAD guys out there, if you're working with like DXF files where the units are undefined, uh, again, I've done it quite a lot, importing a CAD file in and being like, why did this end up here? Turns out I'm using, one unit, someone else is using another unit. Similar kind of problem here. So what I want to highlight here is basically where you can define those units. So over on the left, we actually have Revit. So if you're exporting out the NWC from Revit directly, especially if you have the Navisworks plugin for Revit, right here inside of file readers, there's a little setting down here called coordinates. And this is where you can define the coordinate system that the NWC is going to be exported. And for that, instead of using the project internal, we'll use the shared coordinate system. And if done correctly, when you use that shared coordinate system and plop that into Navisworks, assuming the point cloud itself is also on control, everything should come correctly aligned and you shouldn't have to do any manual transforms whatsoever. You should be sitting nice and golden right there.
Yeah, and I think as a business, like it's super dangerous to not always ask that before your job starts, or you have the opportunity, like make sure you're setting up and agreeing on a coordinate system.
Yeah.
Because
no. Hands down, that is definitely one. I would say the importance of a coordinate system is, I can't stress that enough.
Right, because you saw if you align manually, let's say you align to 3 columns, but those columns were all installed off by 2 inches. Like all of the money and time you spend in doing 3D coordination to ensure that things were not going to clash will have gone out the window. And you'll end up having pipes that are going through part of that column or butting up a duct work against it, and you're going to have lots of issues. And then some PM or someone will say, why do we spend all this money on tech? So a big way to like offset that is just ensuring that everybody in your sphere on this job understands what a coordinate system is, and you know how to export that out, right? Or else it will cause you so much pain down the road. So just
I completely agree. Is that coordinate system should act as the ground truth, on that project that everything should then be aligned to. And even if there's not a coordinate system set up, that's where having a robot or a hybrid instrument comes into play. We can offer to set that coordinate system up, and then other trades on site can say, "Oh, hey, look at that," and then they can tie into it. Perfect world. And as James kind of pointed out, there's certain little steps, and kind of there on the right is another one of the key steps where, again, devil's in the details. When you're bringing in, say, like a Revit project into Navisworks, it'll also give you the option right here to set the coordinate system that's going to be used. Again, a couple little small things, but again, ensuring that when you're either exporting or importing into Navisworks to do that QA/QC process, having the correct coordinates selected is another kind of key little link, in this whole thing. Again, it's given me almost like a couple mini heart attacks, especially when I've imported everything in. They're in 2 very, very different spots, and I'm thinking, hey, did I mess up? Is there, a bus somewhere? And then turns out it was just a little setting like this that we flip it over from internal to shared, and then everything's correct, and then I'm breathing a little bit of a sigh of relief. So that's kind of the big thing is, again, stressing the importance of using the coordinate system as a ground truth. And then a couple little, I guess you could say, points where, if you're either exporting, importing out, this is where it might, choosing the correct coordinate system for your data. So that way everything will come into Navisworks, correctly aligned where it should be. So that's my little piece right there. Let me go ahead. And I guess, Justin, you want to take the floor?
Yep. All right. Thank you. Thank you, Trevor, for putting that together. So yeah, the coordinate system stuff is critical for any of the value of really understanding this, because as I mentioned, if you do a best fit, then you end up with some stuff that's in tolerance and some stuff that's out of tolerance, and that may not be true if you're not using the coordinate system correctly. So what I'll cover is kind of basic Navisworks setup and some different settings. And the process here is going to be talking about what to actually, what we would recommend and what we've seen work well for doing QA/QC. A very common workflow can end up being, or at least when you're using automated tools, is that you think it's, you just take your whole model, you take your point cloud, you just kind of spit it through, and it gives you results. And the problem with that is that, full federated models can end up having hundreds of thousands of parts, down to the bolts and washers, and we don't really want to go through and inspect every bolt and washer against the point cloud. We want to really focus on the stuff that matters, that we care about at the time of the project, and what's going to be the most efficient way for us to determine if the things that we care about are installed correctly. I'm going to go ahead and share my screen.
Yep. Can you yank it, Justin?
I'm going to try to here. Let's see.
Yep, I think you got it.
Okay.
There we go.
Good to see Navisworks here.
Yep.
So what I'll first start with is just a very brief overview of, how to bring in data for Navisworks, and then we can go through and talk about some settings. So Navisworks, very easy to use. We can go through, it's a viewer basically, so I can append basically anything in. So we have lots and lots of different file types. The file that is the most common from Revit is going to be an NWC, a Navisworks cache file. And so that's going to contain kind of the cached information from Revit that really is all the information that Navisworks will need. And so for this, I have all these different models that I can grab, and I can select all, and I can say open, and this is going to load in my geometry effectively. So this is all dependent on the way that you export from your kind of deliverable software. So in this case, like we said, we're doing this from Revit, but there's other stuff mixed in here. So this actually is not only Revit, this is Revit, this is Plant 3D, there's some AutoCAD mixed in here, but because it's Navisworks, because it's a viewer, we can look at all of it together. And we see our geometry. I'm gonna go ahead and do the same thing for our point cloud. And so instead of going through for geometry, I have scan data and I have my point cloud. So something that was talked about in the beginning was the scan data itself. When you collect scan data, it's way easier to cut down the data quality after you've collected it than it is to go rescan if you need more density in your scanned data. So it is definitely recommended to collect lots of data. For working with Verity specifically and kind of the QAC workflow, the more data, the longer it will take to run the analysis. And depending on what we're trying to inspect, we may not need all of the scan data to determine if that I-beam or if that wall is in the right place. With a couple thousand points, I can tell you, or Verity can tell you, if a wall is in the right spot. We don't need 10 million points on a wall to tell you that. And so in this case, this data set that we're looking at, we've gone through and decimated down. We've removed that, so it's only 1 and 3, so that we took out 2 rows and 2 columns, so that it's a third the size, or a ninth the size of the original point cloud. And that's again just for performance time, so that it helps for speeding up that results you get. But we've also made a lot of performance improvements in Verity, so there's kind of a balance there, but that's something to keep in mind. So I'll go ahead and load this in as well. Now in this case, because everything was coordinated ahead of time before we brought it into Navisworks, we actually see that we brought in the scan data and it is all lined up automatically because we're using that shared coordinate system that Trevor brought up. That's a really important thing. That's the most value you're going to get, is if everything is coordinated correctly, because it's going to give you the most accurate results for if things are in the right place or not. Now at this point, we haven't saved this, so we need to actually save the project, and you would go through and you hit save, and this is going to create what's called an NWF, and that is kind of the project file for Navisworks. And I'm just going to make this a temp, I'll just say demo. There we go. And so now it's saved as the project, and then if I close this, then it will open everything up. Some things to look at. So there's some different ways that we can set this up and kind of add value for the project. So one big thing is, especially for anybody who is using point clouds in Navisworks, if you don't know this, this is going to be a lifesaver. And that is going through and actually setting the density of the point cloud. So you can see the point cloud density is like impossible to see unless you actually move around by default. It's very, very difficult. This is like the first thing I do as soon as Navisworks is installed. Is I'm going to go to options, and if I go to interface and under interface click on display, there is this point size option, and I'm going to set that to 3. We've heard people who have used Navisworks point clouds for years and just didn't know that option was available. That makes working in Navisworks with point cloud so much easier. That is the first thing. That is like, if you take anything away from this, it's probably a big one. If you didn't know that existed already, just because that's super annoying that it's so tiny and basically invisible to see it. So that's one just kind of tips and trick. The other thing is that, you know, as far as going into the philosophy for this, is what are we bringing and what are we actually inspecting? So this is a big project, or well, it's not a big project. This is a tiny project realistically, but there's lots of stuff. And so if I want to know, you know, if I'm trying to inspect if it's installed correctly, or if the things that I'm worried about are installed correctly, I want to start with the scope of work I'm looking at, and then work my way into determining if, you know, like what I want to check. So some examples for that are going to come down to the types of data. So and the timing for the scans. So if we look at this data set, I have this pipe system here, and you know, this is something we work with a lot. But we have this pipe system here, and we can see that the scan data is the same diameter as this, what we're looking at here. What we see here is not a pipe. This is actually insulation for that pipe. And so if I hide this, this is my actual pipe. And if I show properties, which I can do right here, so this is actually where this, you know, this object is streamed from AutoCAD in this case. So it doesn't really have a ton of, you know, kind of information. It's mechanical piping, I know that. But as far as like, you know, the certain level of details is not quite filled out. But this thing is the actual pipe. And so when we're doing an inspection, the problem is that if I only look and select this pipe and try and analyze this in Verity, it's not going to line up at all because it's a totally different diameter and in a different position than what the scan data is going to show us. So for this case, when the scan was done, it was done when everything had insulation on it. And so we need to, whenever we're doing QA/QC, we want to compare the state of the situation, so in the point cloud versus the actual versus the model. And so, you know, I don't want to just go through and say, oh, I'm looking at pipes, I'm going to select my pipes and do QAC on my pipes, because they're all going to be very wrong. Even if everything is installed perfectly, which it never is, everything's going to show up incorrectly because the object that is in the scan does not match the geometry that I'm trying to inspect. So that's a really important thing to keep in mind, is that, you know, what we are inspecting with these tools needs to match what's really in the world. And so in this case, I actually don't want to go and inspect. I don't want to inspect. Get back there. The pipes itself. I want to inspect the insulation. The other thing that we can look at for this is the, you know, kind of trying to minimize the number of elements we're inspecting. We don't want to load in, when we run Verity, we're going to look at individual objects. And so if you just select the entire project, and that can be done here in the selection set or selection tree. If I go and I just say, okay, you know, I'm going to grab literally everything that's loaded and go check it, then that could be, you know, 10,000 items, that could be 100,000 items. And that could take a very long time to process. And then even after processing, that's going to take a very long time to review. So we want to cut down what we're looking at. And so some ways to do that are going to be sorting based on different properties. And just some high level concepts for that. You know, if I want to know if this I-beam is in place, if I select this I-beam, if I want to know if that's in the right spot, I don't need to know if the bolts that are associated with this I-beam are in the right spot. I don't need to know if gusset plates are in the right spot. I don't need to know if anything other than the baseline geometry is in the correct spot, because everything attached to this is also going to be out of tolerance if this I-beam is out of tolerance. So, you know, you really need to, like when you're inspecting things, you don't want to just grab everything. You want to think about, you know, what is going to give you the most value for that inspection. The same thing goes for pipes. If I'm looking at this pipe run, I don't really need to know if this elbow explicitly is in the right place, because if this pipe and this pipe are in the wrong place, even if either one of those are in the wrong place, inherently your elbow will be in the wrong place too. So, you know, we don't need to check necessarily if a valve is in the correct place, because if the pipes that valve is connected to are in a wrong place, then so is the valve. So it's again, it's just a mindset of thinking, how can we minimize the number of elements to get us the best results as quickly as possible. And so ways to do that, and in this case, I have a project that we've already kind of set up. in this case, you know, I have and this project is much more built out. So the one we just made was just brand new. It didn't have anything saved in it. The way we can kind of create these things is selection sets. And this is anyone who's familiar with Navisworks and using clash detection, it's the same concept. You don't just grab your entire model and tell me where all the clashes are. You're going to get 10,000 clashes, and that's 10,000 things you need to look at. You're going to go and you're going to make selection sets that's going to say, okay, you know, here are all the mechanical pipes that I care about, and show me clashes with the ducting systems. You know, and that's how you can sort things. It's the same concept. So in this case, we have our sets that we've already created. So you can create selection sets. There's lots of ways to do it. But for this, we have different selection sets. So a really good example of a recommended selection set type is what we've done for mechanical piping here. And you can see what we've done for this set is that we have only the insulation selected, and we have only, like, we don't have elbow selected, we don't have any components selected. We have, you know, it is just the straight sections of the mechanical piping insulation, because if those are right, if everything there is right, then everything associated with it is right. If those are wrong, anything that's associated with that is also wrong. So that's something that, you know, you can go through, and that's just a much more efficient way to do that. Now, to create sets like this, there's a bunch of different ways. I mean, this is kind of the standard Navisworks workflow, but some cool things you can do is with the find tool, it's going through and I say, okay, I want mechanical piping. And you can basically just go through and look at the different categories, look at properties, and define information for those different elements to create and search for similar geometry, and go through and look at that. So if I select one of these sections here and I look at properties, there are different properties that we can look at in here, and then we can say, okay, we want stuff with similar properties. So in this case, it's coming from AutoCAD, so it's a little bit less information than, you know, maybe normally would have if it was coming from something like Revit. But we can go through and we can search for things like this mechanical insulation, right? So if we look at this copy value, and I can go to find items, and I can go look at categories, and basically, I don't want to go take a ton of time to go through and search all this stuff, but we can go and we can look at this information. So if I go to layer, condition equals, and we put this value in theory, when we run this, if we say find all, this is going to be all the things with that same mechanical property. So that, in this case, is that one section. There's, you know, it'd be going through and basically defining all of these different categories to get us the results we want, so that we can then save that with the create, like the create section sets. So I can hit this little create button, and that will save it. But that way you can actually have that, and you do want to save the selections before you go to Verity, because it's very helpful for repeating that search. So that kind of covers the kind of workflow there. The other thing there is, you know, viewpoints are very helpful, so you can go back to different points. But all of this is set so that when you go and you're working with stuff inside of Verity and Navisworks, you do not want to just grab a big chunk of stuff. You want to grab, you know, kind of things that matter to you at the time. So that's also based on schedule. It's based on scope. But we just don't want to grab the whole project. That's a big no-no. So in this case, I have a set here. What I'll do is I'm just going to jump right into this. So I have a little demo set. It's a couple scans. It's a couple elements. And we can do add to Verity, and we'll load this in and we can run it. What we'll talk about after this in the next section is just the, you know, kind of review stuff. And then we will pass this on finally to James for the finishing up for actually, you know, what do we do with the data we find? So we'll run this very quickly and then pass this on to James. Okay, so in this case, I have this, you know, Verity open, and we have geometry that's loaded in, this little split view thing, and we have our scans. So we're going to run our analysis. This is where we can define our tolerances. So if we want to go, in this case, I do 50 because that way something passes. If we leave it at the default 12 millimeters, nothing is a pass. We do indoor because we're inside, and we can run this. So this will process very quickly. And so with this, the key for reviewing this data is just, we want to go through, we do want to review it, even with automated tools. It's just quickly say, you can either just look at it and agree and say approved, or you can make whatever changes necessary to, you know, set it to the right value. All of this stuff is set for, we want to make it as quickly as possible so that we can go and kind of review it. So I have my results here. It's just a little table. So I have 15 elements that were checked, and 5 of them pass. The other 5 are out of tolerance, and then the other 5 are either not found or occluded. So we need to look at those. As far as reviewing things, it is super helpful to just have things side by side. If I can find where I put that, there it is. Windows 11, I have not gotten used to that yet. Close enough. All right, so if I select an element here, I can look at it. And so the review process is starting out just looking at the statuses. So you can sort by status. And so in this case, we can see if it's installed, if it's out of tolerance or pass. Occluded is something where, we don't know. Basically, Verity is unclear because something's in the way. So that would be, if you try and check a pipe that's in a different room from the scans that you've done, it would be occluded. We do not have information. So we cannot tell you if it is there or not there. It's just, we don't know. And so this is purely just looking through, and you either agree with the results. So Verity says that this is out of tolerance. So I tend to agree because of the fitment. It is clearly lower than where it's supposed to be. And so you can say, okay, I approve that, and I've reviewed that, and it is now stored in the system. And that's information that we can keep to say that, it is on to the next section. So we say we reviewed, and we can go to the next element and kind of work our way through it. This is why we recommend, being more strategic with your selections of what you're inspecting, because having a list of 10,000 items that you have to go through isn't really helpful if you only need to really check 100 of those. So to know what you need to know for that moment. And so we can go through and we can look at this, but it is just inspecting it. You can update it. So if you disagree with the fit, or if it's not correct, so in this case, we have this thing, it's not found. That is not true. We see that we do have some scan data. So we'll say it is installed, and then it actually automatically found a good location for it where it's located. And we can see that now that it is installed, it's a pass. And so it really is looking at it. The stuff we are looking for is not found. This is a case, if I go to this view frame, so this element is just not present. If it was, we would have scan data on it. And so because we see the scan data behind it, but none on the surface, we know this thing is not installed. And so that's the sort of stuff we're looking for. There are heat maps, there's other reviewing stuff that we can do in the software, but that kind of covers the process. Is just looking at it, agreeing with Verity, with it saying, with its assessment, or updating that. In either way, you can usually do that in under, it's either going to take a couple seconds to say, yep, that's right, and move to the next one, or take 20 seconds to tweak it to go and say, okay, that's actually what it is, and go to there. So with that pretty much covers the kind of the basic review process. And so then it will transition into actually pushing this out to basically, to people who need to know, because at this moment, you're the only one who knows this information. And so we need to get this into the users, into shareholders' hands. And so I will leave that for James to go over, how we take this data and we're actually doing reports and pushing it into cloud services like Verity for Verity reports and Collage Web.
Awesome.
All right, I guess,
yeah, can you reshare your screen?
Yep, let me go ahead and do that real quick. And then move that out of the way real quick. And then what screen can you see?
I was
the correct one.
Yeah, I can see the Verity report. Can you just click on the PowerPoint, or bring the PowerPoint up?
Yep.
That. Take a second. We're going to dive right into this, everybody. We're not trying to demos is where it's at.
Oops. Did I do that right?
So the thing is, there's kind of 3 areas where how you can deliver data. One is, so Justin just showed working inside of Navisworks, and if you're doing a coordination session with the design team. So imagine you've got Verity, right? And you've gone out and you've scanned a renovation job, and then you want a really great use case is the design model right? So before we start building the building, it can be during pre-construction when you are like bidding on the job, or maybe you're post-bid and you're in schematic design or DDs and you're like, oh, let's compare this to the renovation model. So before we print and go to permit, let's make sure stuff is right. You can do a coordination session and work inside of Navisworks and share your screen and everybody can see it and be familiar with, you know, this authoring software. And whatever issues you find, you can also export that data out as a point cloud, specifically the things that are wrong to the authoring software, whether it's Rivet or CAD, right? It's coming out as an RCP. When you're on a job site, people also need to be able to see the data, and they're not going to open up Revit. They're not going to have Navisworks. They won't even know. They're like, I don't care about that, man. They're going to care about one of two ways: either web-based sharing on their phone, like let me look at the thing, or just a 2D document that says this is how this thing was installed, right or wrong, and here's how far off or up it is or not. A really great way of doing that is we can actually publish to Collage Web, which is a web-based hosting service that you can publish your point clouds, models to, even pull down data, which is great. But you can visualize and show this to other people on the job site, superintendents, field personnel, and they can say, oh yeah, like that's the thing that's wrong. So maybe pull that up real quick and we'll explain that. We are, so FYI, we're building even additional new bridges to A360 Construction Cloud, because obviously it's very important to be able to commit data to Procore, A360's platform, or by email. So you're creating issues. If you find issues, that's a way for reporting documentation, is you click and you go to Procore and log into your job and sends that issue out there, or through A360. Justin, can you quickly click on the Collage Web example?
And let me go ahead and open that up. And
yeah, so it's really nice about this is we actually, so for those who don't know, this is a shell, but we do have a real-time registration software now that works out in the field with the GTL or the GLS, where you can get on control while you're in the field. It fully bundle adjusts and registers as point cloud data, so there is no office work. It's all happening while you were scanning, which is great. And then you can just publish that with the Wi-Fi connection. You can just publish that to the cloud, to Collage Web, and see the job, and people can see what's going on, what's right or wrong, and you can annotate, so you can do some measurements, you can create issues and questions like, hey, what's this? Or it can just be a way for the owner or the superintendent or whomever to see how is the job getting built. Is it like, are these things wrong? And you know, the nice thing with 3D is this is the world we were born into. We were not born into a 2D environment. So humans generally understand a 3D world. So if I have red, yellow, and green stuff, red means it's wrong, and I can look at where it's at. I can go walk over to that thing and be like, oh, this is the thing that's installed wrong. Because really what you care about is you can do all this work, which is automated now, which is great. So it's super fast, finds the issues, but what matters is the person in the field knowing what changes to make if they're building the building, which is very critical. And then on the design side, they could just open this up and look at the issues while they have Revit open, right? Very common way of buildings getting designed. I would say you also still want to create the report from Verity web reports. I guess before we leave, you know, on this, the nice thing is you can turn on, this is an intensity value. You can see the heat map. You can see, yeah, what's right and wrong. You can turn the point cloud. If the point cloud's in color, you can turn on color and turn off the model. And you can increase the point size if it's a low density scan, so the points get bigger, so you can actually see more of like a beam. But also the reporting matters, because from a legal standpoint, you also want to have documentation. Say there's a change order and you're not to blame. You want to say, hey, look, I found this issue. This never got fixed. And the ways to do that is, one, you create the Verity report. You also can submit those issues again through a web-based project management system, right? Which is very critical. Or you shoot an email out. And that's just, a big part of how building contractors, whether you are a GC, MEP, structure, framing, it doesn't matter. How you make money, because fees are commoditized, is risk prevention. So like the companies that make the most profit and remove profit erosion are the ones who know how to manage risk best. That's how you get people get better bonuses, have more money to invest in tech, you name it. It all comes down to, like, when we go into a job, there's going to be problems. We build that into the budget. We're building buildings, but we're hoping we can manage the risk well, so that if we're not at fault, we can prove that, or we can find things and be proactive and know there's issues. We can fix them then and kind of train the job and the people in the project, hey, we're looking at these things. That's kind of one of the points of Verity, is because the heavy lift in the past has been, it's very hard to do this because checking things manually is tough. If you have a robotic total station and you're shooting you're as-building everything, you may not have the time, right? You're being asked to do a lot, you're wearing a lot of hats. But if you can do some layout, then you can run a quick scan, you can automate that process, or you've got whatever terrestrial scanner, even some things with Navis scanner, you can capture the data and run a heat map, or find the issues, and you're doing it in that same day. You want to do it that same day, because then the subcontractors know, oh my gosh, we're all being looked at. Or if you're the subcontractor, you can say, hey, GC, you're doing this thing wrong, right? So by doing this, you are managing risk, protecting yourself from absorbing a change order, and losing money, which you don't want to do. And this is also obviously very good during design, because the last thing you want to do is get a set of documents, and as humans, like, we'll go through and redline and say that wall doesn't look right, but the best thing you can do is layer the scan over it, show all of where the model elements are actually designed wrong. So before you start building the building, those things can get fixed. So while the structure is coming out of ground, you can know those things have been changed and fixed. Because you don't want to, that'd be terrible to tie into, I don't know if anybody here has ever done a renovation, but if you're tying into a hospital or a museum or whatever, you're adding on an addition, the last thing you want to do is find out that the floor height is actually wrong. It happens all the time. Adding on to an additional a new parking deck, and adding a new portion to an old parking deck. It's very common, like probably 50% of jobs. So what's it worth to do this? It's worth every penny. That's it.
Perfect. So with that, I know we're basically almost at time here for our 1-hour webinar, but I guess we'll take this time, we'll stick around for a little bit, probably do about 5 minutes of QA. So at this point, we'll open up the floor. So over in the bottom right of the chat box, 2 things. I also posted a link if anyone wants to check out that little example project, the I-beams. That's a fully shareable viewer, so the link is in there. But let's go ahead and open up for questions. So yeah, floor is everyone. So any questions about anything we've talked about for today, go ahead and shoot them over. I guess kind of one thing I really want to stress is just the importance of this whole thing about coordinate systems. Coordinate systems are absolutely fantastic. I'd say that's probably, I don't know about you, James, I think that's one of the key things to take away from this, and that's kind of the big, centerpiece of having a good construction verification workflow, is making sure you can lay in the groundwork and have, that coordinate system is basically the key link to all of this,
Yeah, it's critical. Yeah, so if you're doing verification, you really do need to tie into a coordinate system. The one time the only area where you may not have to do it is if it's an interiors only job and you're relative to the constraints of the walls. The thing is, then you would be modeling off of the scan. But even then, you still want to have a control system, because you're going to be So yeah, there's no reason not to do it.
Especially now, I feel like hybrid instruments are becoming more prevalent. There's basically, I think there's a big thing of like, hey, like, why just have a robot when we can have a scanner too? We're out there if they're doing kind of, I guess you could say as-built, just using a robot checking singular points, like, scanning gives you way a better sense because instead of just one point, you're shooting millions, maybe even billions.
Well,
Um,
I think exactly. I think most jobs are under, like, most scan jobs are less than 30 scans. So unless you are doing, there are jobs out there you're doing thousands of scans on, but a lot of projects, at least in my past, of like I'm doing it for almost 15 years. You common projects are not doing more than maybe 50, and anywhere from like, and if you're doing slab reviews, so like heat maps for floor flatness, or you are just checking is my working installed right on this floor, you're doing like 10 scans max. So the problem though is then that thing sits there and like just is not being utilized, and
yeah,
that's money off the table. And it's better to have the person in the field who's doing install also doing layout, if that person exists in your in your company, to then use that same instrument. Because what you're
yeah,
trying to do is like all rising tide lifts all ships, and you want the people in the field doing this scanning and layout, not, if you've got a VDC person specifically doing it, they're committed to doing that when they could be doing like modeling work or doing additional analysis to bring a lot of value. Um,
and even more so, just kind of the back. I would make even the argument having your coordinate system in place, not just for those little 30 scan jobs, but I would say the importance of a coordinate system is even absolutely more critical when you're thousands of scans in. Because like I think everyone who's done a cloud to cloud algorithm, they've seen error accumulation. You get 2 millimeters here, 2 millimeters there, that stacks. Next thing you know, by the end of it, like 1,000 scans later, you're like, oh, half a meter, just throwing out some numbers. But I would make even the argument having a coordinate system on even those bigger jobs, even if you are doing mass scanning, that's even more critical to have.
exactly.
Yeah, but even for just doing 20 to 30 scans, like especially if you're doing like more analysis work or just small little captures, having a coordinate system already in place, especially if you're going back, you know, that you have that coordinate system that you can tie into. I mean, again, stressing the importance of a coordinate system, I think that's probably one of the key takeaways, from this webinar. And besides that, another kind of funny one, I wish I could have talked about a little bit was, the data size itself. Like, always a little bit better to have more data than you think you need. That's one of the advantages of all these instruments doing 2 million points per second plus. But on the flip side, also know a little bit about what you need. Uh, Fun comical stories is people who pick up their first scanner that does over 2 million points per second, and then it completely floods their FTP system with all this data, and they're carrying around stacks of hard drives. So, little things like that of scan with the appropriate resolution, the appropriate setups, and again, just producing key, good quality point cloud data in the field that matches, whether or not you're trying to do mass capture for analyzing, or for doing engineering work on like a plant versus, hey, we just need something quick, just for like a proposal or something like that. I mean, any thoughts towards that, James, or any comments?
I don't think so. I think you landed on it, actually. Seriously. I don't think that there been any other, let's see.
Nah, there looks like the questions are pretty quiet. So that's about 5 minutes past the hour. So I think with that, we'll probably wrap up today's webinar, and we'll send the recording out for everyone. So that way, anyone came in a little bit late, you'll have the full recording of today's webinar. And with that, always feel free to email us. We're more than happy. Any questions that come up or, anything like that. If you're interested in the Verity product too, do let us know. We're always more happy to set up demos, trial licenses, etc. So I guess any final closing comments that you'd like to make, James?
No, just thanks for being here. I think if you've got questions on anything, so it can be like, how do we get stuff out of Navisworks, or what is the best scanner to get for this kind of job? We will just give you an honest answer. Or even things that deal with layout. You name it, well, we have done it all. We've lived it all. Even if you have scheduling questions and how to build that in for like 3D coordination, you name it, we will answer that for you. Just reach out to us and we'll make some time. That's all I got.
Perfect. So I guess behalf of myself and the Clearage 3D team, hey, Thank you everyone so much for joining us for today's webinar. And with that, enjoy the rest of the day and happy modeling.